So we'll have a look now, reminding ourselves about differentiation from first principles. Before we sort of do that, we'll just have a look at what limits are. Okay. You would have seen these before, where you have this LIM, and then underneath that X, and then sort of an arrow pointing to a number, and then a function. What this particular statement means is it's saying what is the limit as x approaches 1 of this function 3x plus 1. Now when we're talking about the limits of a function, this quite helpfully just makes it quite clear. The limit of a function is the value that the function approaches as x approaches a given value. Okay, so if we have a look at this particular case, say the function was y equals 3x plus 1. As x approaches 1, okay, we can see we're looking at what the value is. Okay, and so it's just a matter of substituting it in there. If the function is continuous at the point, okay, then the limit exists and can be found by direct substitution. Okay, so that's an important thing. Okay, if it exists, then we can just substitute and we'll get a value. And so we can see with this one, it's a nice continuous function and there's no gaps in there at all. So we can just substitute the x with the value of 1 and we get 4. So the limit is value of 4. If the function is discontinuous at the point, so maybe it has a hole in it, like there, or maybe there's a gap, okay, the limit will exist if the function is approaching the same value from the left as from the right. So with this first one here, if we're going from the left, okay, and approaching this value of 2, then it seems to be approaching this value 3. If we come from the right, it's approaching the same value. So even though there's a discontinuity here, the limit exists because it's approaching that same value from the left as from the right. But in this case here on the right, then we can see, okay, as we come from the left and we're approaching this value of x of -2, it's getting closer to this y value of 3. But if we come from the right, then it's approaching this value of 5. Okay, so because it's got this gap here, the limit does not exist at that particular value. Okay, so in terms of finding the value of limits, then we can sort of look at the function that's given and we can pretty well determine if the function is going to, if we can just do a direct substitution. So for this one here, first one, we're finding the limit of x squared minus 3x as x approaches 5. So we can look, just looking at that function, putting a value of 5, there's going to be no issue with getting a value. So we can put that in there and just calculate it, and we can see that it just comes out at 10. So the limit is 10. For the next one here, okay, we're looking to find the limit of this function as x approaches 0. So we look and think, if we were to put 0 in there, is there going to be a problem? Well, there won't, because we'll be left with 6 on top and 3 on the bottom. We can get a number, we'll get the value of 2. So that's okay. Okay. However, there will be an issue if we find that by substituting we end up with the denominator is equal to 0. Okay, which would be the case if we were looking at, for this one here, B, where x is approaching, say, -3. Then we would have a problem. Okay, and then in those cases, we need to do something a little bit different. Okay, so we can see that by substituting -3 in place of x, the denominator will be 0. So we just need to go for an extra step and think, well, it doesn't mean it doesn't exist. It just means that we may need to look at doing some algebra. And so if we look at the numerator, being a quadratic, okay, and a nice sort of straightforward one, we can factorise, okay, into x plus 3 and x plus 2, which means that we can cancel our x plus 3s out and we're just left with x plus 2. So then if we substitute the x with -3, we end up with a value of -1. And so the limit does exist, being a value of -1. That would be, this kind of situation would be like this one here, where it is in fact a straight line, except it has a hole in it. Oops. Except it has a hole in it there, that discontinuity. So even though it looks like a fairly complex function, x squared plus 5x plus 6 over x plus 3, for the most part, it is just the straight line graph of y equals x plus 2. It just happens to have that discontinuity at that value of -3 for x. So in those situations, we do a factorisation and cancel, and then we can work through it. Okay, so there won't really be much in the way of questions associated with those sort of things. We sort of more looked at that last year. But it does lead on to differentiation from first principles. And if we have a look at this kind of setup, we've just got this curve, and we have, say, 2 points there, P and Q. Point P has an x coordinate, which we'll just call x, and then P and Q are separated horizontally by some distance h, okay, which would make the x coordinate of point Q as being x plus h. The y coordinates then would be found by substituting those into the actual function. So if we've got f of x, then the y value of point P will be f of x, because we're just putting an x in place of x. But then the y value of point Q would be found by putting x plus h in place of the x in the function. And so that's why it's got f of x plus h. And so the gradient, if we were to find the average rate of change, if you like, between P and Q, then we're just looking at rise over run between those 2 points. So the rise is your vertical distance. So we're subtracting the y value of P from the y value of Q. So that's what this here represents, f of x plus h minus f of x. So that's our rise. And our run is the distance horizontally between the 2 points, which is h. Okay, and so this f of x plus h minus f of x over h is the gradient of that line, which we call a secant, okay, between points P and Q. The whole point of differentiating from first principles is we're thinking to ourselves, what happens as Q and P get closer together? So what we're looking is to find what is the limit of that gradient, okay, as our h value approaches 0, because that's essentially what we want. We want to know the instantaneous gradient, if you like, the instantaneous rate of change. Okay, the secant joining P and Q, that line, that represents an average rate of change. We want an instantaneous at any point. So we want h actually to be 0. So that's where the limits come into it. Okay, we're finding the limit of our gradient function as that h, as that horizontal distance, the run, approaches 0. Okay, and so that's where this is here, right? I don't know if it's going to highlight nicely or not. But f dash of x, okay, the gradient at point P, will be the limit as h approaches 0 of our rise over run, f of x plus h minus f of x over h. Okay, and that's what we call the differentiating from first principles. We know it is the long way to do it. Okay, it's much easier just to use our rule, which we'll come across, but we still need to know how to go about doing that. Okay, and so we can apply that to, if we have a look at, will we worry about this example? Don't worry about that example, skip over that. Okay, all right, so if we look at example 8, finding the gradient of f of x equals x squared minus 1 at the point where x equals 2. We'll skip a, so we won't worry about sketching the graph and using the tangent. We'll just do it by differentiating from first principles. Okay, so we need to first of all find what the rule is for the derivative. Okay, and so the first step is to write out the rule according to first principles. Okay, our derivative f dash x is equal to the limit as h approaches 0 of our rise over run, f of x plus h minus f of x over h, provided h, of course, is not equal to 0. So what we do then is we have that function, which was x squared minus 1, so f of x is equal to x squared minus 1. And the first part of our first principles is f of x plus h. Okay, so f of x plus h, okay, is wherever we see the x, we replace it with x plus h. So f of x plus h will be x plus h squared minus 1. Okay, so that's this first part here. Then we've got minus f of x. Okay, well, f of x is this here. Okay, so that's this second line then. Okay, we've got x plus h squared minus 1 minus, we just need to make sure we put in brackets our f of x, which is the x squared minus 1. And then we can remove the brackets, which is just going to change the sign of those inside. And of course we expand the x plus h squared, so it becomes x squared plus 2xh plus h squared minus 1, and then we've got minus x squared plus 1. And so we want to cancel anything that we can there, so we've got the x squared here at the front, minus x squared here, so that leaves, that sort of wipes them out. And then we've got minus 1 plus 1, so that eliminates that. So what we're left with then is just 2xh plus h squared over h. Okay, so we're finding the limit now of something a little bit simpler. Okay, but of course we still don't want to just directly substitute the h because we've got still the h on the bottom. So we take out the factor of h, which is common to both these terms, and then we can cancel it out. And so what we're left with then is the limit of 2x plus h as h approaches 0. Okay, then we can just substitute 0 in place of the h, and we're left with 2x. So this 2x then represents the gradient of our original function. Okay, so the original function was the parabola x squared minus 1, and so the gradient function is that straight line graph y equals 2x. Okay, so what that means then, of course, we can find the gradient at any particular point on that original function, x squared minus 1, by substituting x with the particular value we want. But we want to know what the gradient is when x equals 2. So here we've got our gradient function 2x, and so we just replace the x with 2, and so we know then 2 times 2 is 4. So the gradient then at x equals 2 will be 4. Okay, so the crux of differentiating from first principles is this part here. Okay, we start with the rule for it, and then using whatever the function is that we're given, we're replacing with x plus h, and we're just using those in order to actually work through until we can find the limit. Okay, so is that okay? Is it, I'm sort of coming back to their memory a little bit, and hopefully is gelling perhaps a little bit better than perhaps it did last year. Okay, it's still a long way to go about doing it, but yeah, and it's quite common for there to be a question in the exam on that. Okay, we'll look through the next one here, doing the same thing, right? So use first principles to differentiate x squared minus x. Okay, so g of x instead of f of x, but it's the same idea. Okay, our rise over run would be g of x plus h minus g of x over our h value. So g of x plus h then is just replacing in our original function of x squared minus x, replacing the x with x plus h. And so put those in there, expand it, collect any like terms that we can. And so we've got x squared plus 2xh plus h squared minus x minus h. That then goes in place of the g of x plus h. And then after that, we're subtracting our original function g of x. So that's the x squared minus x. Remove the brackets, collect any like terms, and find that some terms will eliminate. Okay, and so we can see on this fourth line here, we're left with finding the limit as h approaches 0 of 2xh plus h squared minus h. Again, what we should find is that every term, there's a h in there that we can take that out as a common factor. So when the h is taken out from here, we're left with 2x plus h minus 1. Okay, these h's here, top and bottom, will cancel. And we're left with 2x plus h minus 1, and then when we replace the h with 0, we get our derivative of 2x minus 1. Okay. So is that all right? Okay. So what we'll do then, we can just, you can, if you're happy with what you've done in 7a, you don't necessarily have to go through all of that, but if you want to keep going with that, that's fine. But otherwise we'll go on to 7b and just work through those. You could perhaps work through every second question, would be fine. So then next week we'll sort of get into finding derivatives using what's called the chain rule, and that will be something which will be new for you. Okay, so 7b, I'll leave it with that.